for that, let us go back and just revisit the Pascal strength for instance. 1, 1, 1, 2, 1, 3, 3, 1, 1, 4, 4, 1, 1, 5, and 5. We'll complete later on. You will get the purpose by the Pascal strength. So now, what was required is the polynomial was like in x raised to n form. Then we know that when we replace it something like cos we will get cos n theta, and then we needed the coefficient to be like this. This was something required. So this gives us an idea that we need to convert cos the power n as some degrees. Some kind of this motivation is required. So what we will do is first of all consider, let x be equals to cos theta plus I sin theta. So if this is the value of x, first of all it should be clear that 1 upon x will be cos theta minus I sin theta. Anyone has a doubt why this is true? If x is cos theta plus I sin theta, then 1 upon x is cos theta minus I sin theta. All you need to do is do the reciprocal, then take the rationalization. In the denominator you will get 1 and this will be the numerator. So now if I just add these two things, x plus 1 upon x, I will get to a result of twice of cos. Keep this thing as it is. Now parallelly we can do one more thing. Like if this is the value of x, the value of x raised to n would be cos raised to n theta plus I sin n theta by numerator theta. And similarly the value of 1 upon x raised to n would be cos n theta minus I sin n theta. Now if you will just add these two, you will get x raised to n plus 1 upon x raised to n is twice of cos n theta. Keep this result also with you, and we also have this particular result. All clear here? Now what we will do is take this thing, x plus 1 upon x, it's just an expression, and take the power n and expand it using the binomial theorem. So when we use the binomial theorem, the first term that we will get is x raised to n. Then we will have nc1, one power reduced from the first term and the other one given the one power. Then we will have nc2, first term reduced with 2 power, the other term got the 2 power. Okay, now in the middle there will be something very nice, it's the middle terms. It will depend on whether n is odd and even. We'll get back to that later. That's why I have drawn that Pascal triangle. Let's now focus on the last few terms. So nc n minus 2. So x will be raised to, I think, twice. 1 upon x will be now n minus 2. And nc n minus 1, x raised to first power, 1 upon x to the power n minus 1. And finally nc, that's basically 1, and we will have 1 upon x to the n power. So this is a long expansion, and that is the reason why I have written many of the terms. You will get to know just now only. So now look carefully. What I am going to do is group the terms. The first one grouped with the last one. So what is the first term? X raised to n, and the last term is something 1 upon x raised to n. So if I just club them together, I have x raised to n plus 1 upon x raised to n. Something nice. Now the second one clubbed with the last second. Now look carefully. This coefficient nc1 is always equals to ncn minus 1. That you can even figure out over here. 5, 5, 4, 4, 3, 3. You can just figure out, or you can just use the what we say the definition of NCR, and you can just get that yes, the coefficients are always equal. So I can just write like any one of them, like it be NC1 taken common. Now look at this thing. What is this simplified to? It's x raised to n minus 1 and it's 1 upon x. So overall it is x raised to n minus 2 in the numerator. And here the same thing is there, but it is 1 upon x raised to n minus 2. You can see it's n minus 1 and then minus 1 will also get. So combining this two, I can nc1 I can take common, and I will have x raised to n minus 2 plus 1 upon x raised to n minus 2. Similarly, this one will be like this way, nc2, and inside what I will have, anyone? X raised to n minus 4 plus 1 upon x raised to n minus 4. Now, here what is this thing will come in play. So, like we are grouping the terms. So it's basically simple, like if I have 5 terms, the first and last are paired, this and this are paired, the middle one is left. So why is this happening? Like we can just look over here also. So just taking this two as example, these are containing it's for 4 and this one is 5. So when the power is even, the binomial expansion contains odd number of terms and always one term would be left. This and this are paired, this and this are paired, this one is left. But when the power is odd, the binomial expansion contains even number of terms and all of them will be grouped perfectly. You can see the pattern. So doing that thing over here, so I have to just break it down like this way. For even something different will end and for some odd it will different. So to understand that thing, we have to focus on the middle part. As you can see that from both the sides we are getting to the middle part. So we have to mainly focus again on the middle part. So let's look what is happening. So what we know is that this will contain odd number of terms. The middle term will always be left. So for this to contain odd number of terms, n should be even. So let us first consider when n is even. So I will just write some few terms. So I'll just first of all write nc n by 2 minus 1 x raised to subtract, we'll get n by 2 plus 1. Then I will get 1 by n to the power n by 2 minus 1. nc n by 2 x raised to n by 2 1 upon x raised to n by 2 plus nc n by 2 plus 1 x raised to n by 2 minus minus 1 and 1 by x raised to n by 2 plus 1 and this. So this is what we get middle three terms of when n is even. You can, if you want to just cross check it, you can cross check from here. Like okay? So now this both will get paired up together. So they will just give us as nc n by 2 minus 1. This would be at last x square plus 1 upon x square. This both paired, and this one will be just constant. nc n by 2. No x will be remaining in there. So this is when n is even. So this particular thing will end up with this thing when n is even. And for when n is odd, the middle two terms will be like nc n minus 1 by 2 and something. This thing I am already doing. It's going to be x only, and nc n plus 1 by 2, and in that case I will have 1 by x. This will be the middle two terms. And again, these both coefficients would be same. I can just take any one of them common, and I will end up with something like this. So these are the two endings that I will get for this particular expansions according to n is even or odd. Okay. So now what I will do next is I will use this result that x is 2 n plus 1 upon x is 2 cos theta. So I can just replace it over here. So what I will get is twice of cos n theta. Then I will have nc1 twice of cos n minus 2 theta, and at the end, like if whatever the ending is, suppose I take the odd ending, I will end up with nc n minus 1 by 2 twice of cos theta. And if it's the even ending, you can just imagine here I will have twice of cos 2 theta plus this particular term. These are the two end terms that I will have, this and this. Now look carefully over here, x plus 1 upon x was twice of cos theta, the power is n. So it can be also given over here. So here we are going to have 2 raised to n cos n theta. So now you can see we have cos n theta, and in the front of it, it's all the n theta, but now it are multiples of theta. So now 2 raised to n from here will go to division to all of these terms, and you can see that all of each of these terms will give us 2 common. And even in the even case also, this constant will give us a 2, and in the odd it's obviously it's going to give a 2. So taking all that 2 common, already we have 2 raised to n in the denominator. We can just figure out that we will have 2 raised to n minus 1 sitting in the denominator. So we can see that cos n theta has got this particular expansion, and whether it's even or odd, no matter, the cos n theta is going to contain the coefficient of 1 upon 2 raised to n minus 1.